All right, let's go back to talking about functions. Remember domain and range. Remember that domain was the set of all the inputs and range was the set of all the outputs. Let's just make sure that we have it in the notes again. Okay. The domain of a function is the set, and that set is important, of all the inputs. And the range is the set of all the outputs. All right. So that's what we're going to be using in this video. In this video specifically, we're going to look at analytical ways of answering this. And in the next video, we'll talk about a graphical way of representing domain and range. Okay, so let's start with example 2. Find the domain and range. Oftentimes, I'll abbreviate this D. And range, I will often abbreviate it, you guessed it, R. R, not D. For the relation that's given by the ordered pairs 2, 10, 3, 10, and 4, 20. All right. Now, we just had a previous video talking about interval notation. We're not going to use interval notation because we don't have an interval, right? These are just 3 points. An interval means everything in the region, right? If we're looking at the number line and we have this interval right here, this means an infinite number of numbers, infinite amount of numbers between those 2 points. We don't have that here. We're not going to use interval notation. We're actually just going to use set brackets. So these right here, these brackets right here, these mean a set, which is why we used it in set builder notation. But here, we don't need to use anything fancy because we can just list all of the things in the domain. The domain is all the x's, right? It's just 2, 3, and 4. That's the domain, the set containing the numbers 2, 3, and 4. The range is a set of all the y values, 10, 10, and 20. We don't have to write 10 twice though. Okay. Only write 10 once. And remember that this is still a function. A function means each input, each question can only have one output, one answer. So 2 only goes to 10. 3 only goes to 10. It's like a multiple choice exam, right? Different questions can have B as the answer, but each question you can only shade in one bubble. All right. If there's repeats in the output, that means it's not 1-to-1. That had to do with the horizontal line test, if you remember that. Okay. So that's our domain. That's our range. Let's do some more complicated ones though. Example 3. Find the domain for the following problems. Let's start with f of x equals x squared minus 1. This is a parabola. Okay. Later on, you're going to get a little bit more comfortable with graphing. And you could identify that if we graphed it, it would look like this. But we're not really there yet. We're going to look at the domain. The domain is the set of all the outputs. Every number I can plug in here. So I can plug in 1, 2, 3, 2.5, 2.1. Think of any number you can possibly think of, and I can plug it in here. It's a real valued function, so let's only think of real numbers, no complex numbers right now. Any real number you want, we can plug in, right? I can plug in any real number and get an output. Okay? So for the domain, we're actually just going to say all real numbers. It's negative infinity up to positive infinity. Another way of writing that is using 2 vertical slashes to write the letter R. 1 vertical slash, 2 vertical slash, capital R. This means all real numbers. All right, and that's all there is to it. Do another problem, part B. G of x equals x plus 1 divided by 2 minus x. We can't plug in anything we want here, right? Note that g of 2, if we plugged in 2 here, we'd get 2 plus 1 divided by 2 minus 2. That's 3 over 0. Oh, that's not good, right? That's undefined. Here's a number where we plugged it in and we didn't get a real output. In the previous one, we could plug in anything and get a real answer, but in this one, we can't plug in anything. I gave you an example. So what are the things that we can't plug in? Well, we can't plug it in when the denominator is equal to 0. So not everything works, right? It's undefined when the denominator is equal to 0. And the denominator is 2 minus x. Add x to both sides. We're going to get that this is undefined when x equals 2. Now, everything else works. So this is for everything except x equals 2. All right? Find everywhere except x equals 2. So we're going to say our domain, if we look at it on the number line, is everywhere except 2. So everything bigger than 2, everything less than 2. Now we can either write that in interval notation, negative infinity to 2, union 2 to infinity, or set builder notation. Set of all x such that x is not equal to 2. These are the only two acceptable ways of writing your answer here for full credit. All right, we will be using this notation. Let's do another one because other problems can arise. H of x equals the square root of 7 minus x. So again, let's do a little experiment, right? H of negative 3, for example, is the square root of 7 minus negative 3. That's 7 plus 3. That's 10. All right, this is defined. All right, it's defined here, but it's not going to be defined everywhere. Right, what if we plugged in 12? We get the square root of 7 minus 12. Square root of negative 5. This is not real. This is an imaginary number, okay? So again, with this example, our domain is not going to be all real numbers, because here's an example. 12 is an example of something that doesn't give us a real output. We're looking for all the inputs that give us a real output. So when are we going to have something real here? It's going to be real when we're taking the square root of something that's not negative, right? A negative inside the square root makes it imaginary. So it's going to be real when the inside is not negative, when it's at least 0. What's the inside? The inside is 7 minus x. Now you have to solve this inequality, okay? We can add x to both sides. Left-hand side just becomes 7. The right-hand side, 0 plus x, is just x. And remember, this is the same if 7 is bigger than or equal to x is less than or equal to 7. Which on the number line, if 7 is over here, we have everything that includes 7, so use a bracket, and is to the left. In interval notation, the smallest we can get is negative infinity. The biggest we can get is 7. 7's included. Infinity and negative infinity are never included. Or we could write this in set builder notation. The set of all x such that x is less than or equal to 7. That's our answer right here. So let's summarize for domains and ranges. In general, for this class, and there are exceptions for other functions, but for this class, the domain is usually going to be everything except where we have some problems. Okay. One way that the problem can happen is the denominator of a fraction is 0. And this is what we saw in part B, right? It was all numbers except when we divided by 0. It was all numbers except when that denominator equals 0, and that's how we found it. We looked at the denominator, 2 minus x, found when that was equal to 0, and said, all right, it's everything except that. The other thing that we're going to really have to watch out for in this class is when the radicand, and radicand just means inside of a square root of, when the radicand, let's say, is negative, because that's not going to be real. And let's make a side note, the index is even. There's a lot of words here, but when I say even, right, some examples are square root, fourth root, right, sixth root. The index is that number up here. All right. So that's what I mean when I say index. So cubed roots are fine, right? Because the cubed root function kind of looks like this. Cubed roots are defined everywhere, but square roots look like this. They're only defined for positive x's. So this second one, when the radicand is negative, that has to do with this example over here, example C, right? We want the inside to be positive or 0. If the inside is at least 0, then we have a real number on our hands, okay? These are the main things to watch out for. Look at denominators, look at the inside of radicals. We'll do some more problems on this in the last video of this section, okay? But in the meantime, good luck.